Let me welcome you to this lecture. We are now familiar with all the fundamental aspects of symmetry and group theory, and we know the contents of the character table, as well as we know how can we derive all these informations. At the same time, we have also learned how we can find out the symmetry of different degrees of freedom of a molecule. That is, we have learned how to find out the symmetry of the translational modes, rotational modes, as well as the vibrational modes of a molecule. Now, during this lecture, we will learn one very important application of symmetry and group theory. That is, we learn how these symmetry selection rules can be derived, or how we can apply these rules and find out which particular transition, or whether any transition between two states, energy levels is going to be symmetry allowed or symmetry forbidden. Say for example, you have already learned that DD transitions in transition metal octahedral complexes are symmetry forbidden because the transition from say T to Z set of d orbitals to EZ set of d orbitals are not symmetry allowed, and that is why DD transitions are essentially weak. Now, how do we find out if uh, how can we verify whether it is correct or wrong? Can we can do this by using group theory, as well as any transition between any two uh, state, the molecule, energy state of the molecule can be found out by these rules. And we will also learn how, by using the same procedure essentially, how we can find out whether a particular vibrational mode of a molecule is going to be uh, IR active or Raman active. So let us begin with this. So we know that when we have two energy states of a molecule, psi 1 is the ground state and psi 2 um, is the excited state. Now, if we have the energy of psi 1 to be equal to say E1, and energy of psi 2 is equal to E2. Now, if we have a transition, if we excite an electron from psi 1 to psi 2, now the wavelength or the uh, frequency of the transition is essentially given by h nu equal to E2 minus E1. This we have learned as part of spectroscopy. Now, the intensity of the transition is essentially determined by the symmetry properties of the molecule. That is, intensity of this transition, or how intense this transition is going to be, whether this transition will essentially occur or it will not occur, is essentially proportional to an integral. That is, you have to take the two wave functions, psi1 and psi2, and you have to use an operator which is known as the transition moment operator, and then do integration of these two wave functions in the space d tau. So now this intensity is proportional to this integral essentially, and if now this integral is equal to 0, then the intensity is going to be equal to 0, or we can say that the transition is going to be now symmetry forbidden. But if the integral is non-zero, then the transition is going to occur and the intensity will have non-zero value essentially. So now how do we find out whether this transition is going to be or this integral will be equal to 0 or non-zero, is by using symmetry, is that one needs to do direct product, because we can find out because if psi 1 and psi 2 are two uh, two states of energy states of the molecule, then these states can now be basis for different irreducible representation of the molecule. So we can find out how the psi 1 transforms as which particular irreducible representation of the point group, then how psi 2 transforms as which particular irreducible representation of the group, as well as we can find out how this transition moment operator can also transform as, and then we can do a mathematical procedure known as the direct product of these irreducible representations. And if this direct product is if this direct product of these irreducible representation essentially, which forms basis for this electronic states as well as the transition moment operator is for is the totally symmetric representation A1, then we can say that this integral is going to be non-zero. So what we have to do, we have to find out how this psi1 transforms as which irreducible representation of the point group, and psi2 transforms as which irreducible representation of the group, as well as we also have to find out how mu transforms as, that is the transition moment operator transforms as in that point group. And then when we do direct product of these essentially, and if this direct product is equal to A1, then we can say this integral has non-zero value essentially. So this is what is the procedure that we have to stick to. So now we have learned what is direct product during our discussion on matrices. We have seen that when we do direct product of two matrices, essentially the dimension of the matrix will increase if we do direct product of matrices of order more than equal to 1. So we did, for example, when we did direct product of these two matrices, as answer we got the matrix So this is the result of direct product of these two matrices. That is, when we did direct product of these two matrices, essentially we we have mentioned also that the symbol that we use to indicate direct product between two matrices is this, a cross sign with a circle, and the result of this direct product is essentially this one. Now we should also remember that we know the characters of different matrix representations for different symmetry operation in all the irreducible representations. So we have found out the characters of the matrix representation for different symmetry operation in the irreducible representations, but we do not exactly know the matrix representations for different symmetry operations in all these irreducible representations, because we have only derived the characters of these matrices. So that will not allow. So if we now, since we have to do direct product of these matrices and the matrices representing different irreducible representations, and since we do not know the matrices, we run into a problem, and this problem can now be simplified if we look at the character of these resulting matrix that we obtain after doing direct product of these two matrices. If we see now the character of this matrix, the first matrix is essentially equal to A11 plus A22, while the character of the second matrix is B11 plus B22. So when we multiply these two terms, we will get the character of the resulting matrix over here, that is equal to A11 B11 plus A11 B22 plus 22 B11 plus A22 B22. So in order to derive the character of the resulting matrix that we obtain after doing a direct product of two matrices, we see that we don't need to know the entire matrix, and we only have to multiply the characters of the two matrices which we are doing a direct product, and that will essentially give us the character of the matrix that we are going to get after doing the direct product. So this simplifies the mathematical procedure essentially, and now we can find out, because we know the characters of the A1 for different symmetry operation for the most symmetric irreducible representation, that is A1, because the characters of all the symmetry operations in A1 irreducible representation has to be equal to +1 +1 +1, and that simplifies the mathematical procedure for us. So let us now do an exercise, or let us now find out whether to illustrate this, we can find out whether this an electronic transition in, say, C2B point group is allowed, or symmetry allowed, or symmetry forbidden. So let's take the C2B point group. Once again, let us write the character table of C2B point group. So this is the totally symmetric irreducible representation, then A2, then B1, this is -1, 1, -1, 1, -1, -1, 1. That is B2. So if we look at the different basis functions, we know Z transforms as A1, and B1 transforms as X, B2 transforms as Y, A2 transforms as RZ, B1 transforms as RY, and this transforms as RX. Similarly, the quadratic basis functions, this is the Z basis for Z square as well as X square and Y square. Then this forms the basis for XY, A2, and this is XZ, and this is YZ. So these are the basis functions that we have already derived for the C2B point group. Now let us figure out whether any particular transition. So if we have to a transition from a wave function psi1 to say psi2, now let us assume that psi1 forms the basis for A2 irreducible representation, and psi2 forms the basis for B1 irreducible representation. So now when we try to find out this integral, that is psi1 mu psi2 d tau, which should be equal to non-zero, which must be non-zero for this transition to occur, or for this transition to be symmetry allowed, we will find out the direct product of these transitions, of these irreducible representations, which forms basis for these wave functions essentially. So now we should also know what is mu, which is transition moment operator. Essentially, there can be different transition moment operator for different kinds of transitions. When electronic transitions occur, we have electric dipole moment operator. Similarly, we can have also magnetic dipole moment operator, like for spin transitions, and we can also have polarization tensors for polarization transitions that we will see here how these operators work. Now for electric dipole moment moment operator, essentially we can use these, because this mu can be separated, that is as mu x, mu y, and mu z. That is on different directions, on different the transition can happen, and this can essentially be separated. These mu x, mu y, and mu z. And these mu x, mu y, mu z essentially, or this electric dipole moment operator along different directions, essentially transforms as, again, they form basis for the irreducible representations as the different Cartesian axis forms basis. So mu x will essentially be transformed the way x gets transformed, mu y will transform the way y is transformed, and similarly mu z gets transformed the way z uh, coordinate gets transformed in that particular point group. So now here what we have to do is that we have to find out three integrals, not one, because mu x, mu y, and mu z can be separated. So we have to find out this one, that is psi 1 mu x psi 2 d tau. Similarly, we also have to find out psi 1 mu y psi 2 d tau, and we also have to find out psi 1 mu x psi 2 d tau, psi 1 mu y psi 2 d tau, and psi 1 mu z psi 2 d tau. So if any one of these integral are non-zero, then the transition is going to be allowed essentially. And if now this particular transition is if this integral is non-zero, that is when we take mu x as the dipole transition moment operator here, then we say that particular transition is x polarized. So similarly, if this particular integral is going to be non-zero, then we will say is going to be the transition is essentially y polarized, and if this integral is non-zero, then we will say that the particular transition from psi 1 to psi 2 is essentially z polarized. So we will find out, and for that we have to essentially do direct product of psi 1, psi 2, and mu x. So that is because we assume that psi 1 is essentially psi 1 transforms as A2, psi 2 transforms as B1. So psi 1, instead of psi 1, we will write A2, direct product, mu x, x transforms as B1, because x transforms as B1, so we write B1 over here, and then psi 2 transforms as B1 we have written. So this will give us, you will see, A2 into B1. Let us multiply the characters of A2 into B1. So 1 into 1, that will be equal to 1. 1 into minus 1. So let's find out what is A2 into B1 will be equal to, characters of identity is going to be equal to 1, and character of C2 will be equal to minus 1. Character of sigma xz is also going to be minus 1, and character of sigma yz is going to be equal to plus 1. So that is 1 minus 1 minus 1. 1 is equal to essentially B2. So A2 into B1 is equal to P2. So we have B2 now direct product with B1. So we have found out this part of the calculation, and now we have to do the result that we have obtained by doing direct product of A2 with B1, that is B2, and then we have to do the direct product now with B1 to find out the answer. So this is going to be equal to B1 into B2, 1 into 1. It is going to be 1 over here, and minus 1 into 1, this is going to be plus 1 for C2, and 1 into minus 1, minus 1, minus 1 into 1, minus 1, which is going to be equal to 1, 1, minus 1 is going to be equal to A2. So this transition, that this we have seen that the answer that we get here is equal to A2, which is not A1. So that is why now we can say this transition from psi 1 to psi 2 is not x polarized, or the transition probability along the x direction is equal to 0. So now let us find out whether this integral, the second integral, is non-zero or not. So psi 1 we can write again A2 cross mu y transforms as b1 and y transforms as b2 and then we have b1. So a2 into b2, we'll see what is the result of a2 into b2, that is a2 into b2 is going to be equal to a2 into b2, 1 into 1, 1, 1 into minus 1, minus 1, minus 1 into minus 1, last one, minus 1 into 1, 1, minus 1. So a2 into b2 essentially gives us 1 minus 1, 1 minus 1. So 1 minus 1, 1 minus 1, which is equal to b1. So b1 into b1. Now when we do b1 which multiply b1 with b1, let's see what we get. So b1 into b1. If we multiply the characters of b1 with again the characters of b1 itself, so 1 into 1 will be equal to 1. Minus 1 into 1 plus 1. 1 into 1, 1. Minus 1 into minus 1 plus 1. So when we multiply a particular irreducible representation, or when we do direct product of one irreducible representation with itself, then we always get the most symmetric representation as the result. That's what we see over here. That when we do b1 with b1, we get answer equal to a1, and now we see that this particular integral is essentially we get this forms the basis for the most symmetric irreducible representation, or that is the AY irreducible representation, and that is why now we can say that this integral is going to be non-zero, and this transition, that is from psi1 to psi2, is essentially symmetry allowed, and it is Y polarized, we have seen. Now we will also find out the last integral over here, whether this integral is whether it is 0 or non-zero value it has. And psi1 again we write a2 mu z is equal to a1 into b1. So that is going to be, when we do multiply a irreducible representation with the most symmetric irreducible representation a1, then we will always get answer equal to a2. So you can check that. So that is when we multiply a1 and a2, 1 into 1, we will get 1, 1 into 1, once again 1, 1 into minus 1, minus 1, 1 into minus 1, minus 1. So when we multiplied a2 with a1, we got the characters of a2. So whenever you multiply an irreducible representation with a1 representation, whenever you do direct product of an irreducible representation with the most with a1 irreducible representation, you will get the irreducible representation as the answer. So a2 into a1 is going to be equal to a2, and then when we do a2 into b1 over here, what we will get, let's see what we get when we do a2 into b1. So a2 into b1 essentially gives us a2 into b1, 1 minus 1 minus 1 plus 1, which is equal to b2. So what we have seen over here, that this transition is symmetry allowed, because we know that we have found out that that it has non-zero, this integral, this particular integral has non-zero value, as this integral forms basis for a1 irreducible representation, while these two integrals actually do not form basis for a2 irreducible representation. But since one of these three integrals forms basis for the most symmetric irreducible representation, and that is why this transition is going to be symmetry allowed, and we can also say that this transition is Y polarized, as only this particular integral has non-zero value. So that is how we can find out whether a given transition, whether it is electric transition or whether it is magnetic transition, is symmetry allowed or symmetry forbidden. So let us now deduce how we can find out whether a given fundamental mode of vibration in a molecule is IR active or it is going to be Raman active, because for the water molecule we have done already, or we have worked out the different symmetry of different modes of vibrations in the water molecule. There are three vibrational modes in water molecule, and we have seen that two of the vibrational mode has so two of the vibrational modes transform as A1 irreducible representation, while one of the vibrational mode transform as B1 irreducible representation. Or we can also say that the symmetry of two of these vibrational mode are A1, while the symmetry of one of the vibrational mode is B1. So then we know the symmetry of the vibrational modes. So since we know the symmetry of the vibrational modes, now we can work out whether these vibrational modes, among these vibrational modes, which one is IR active and which one is Raman active. So to do this again, we have to find out because the molecule as such in the initial state remains in the most symmetric state, that is the ground state in the molecule is A1. We can say that the ground state in the molecule forms basis for the most symmetric irreducible representation, that is the A1 irreducible representation. So the ground state here is going to be A1, and the vibrational mode for which we want to find out the irreducible representation is going to be the for which we want to find out the whether it is IR active or Raman active is going to be the excited state, and so that is going to be the these are the excited states, going to be the excited states. And let us so find out psi 1 again, mu x, psi 2, d tau, these three integrals. Mu y, and if any one of these three integrals has non-zero value, we know that the particular vibrational mode is going to be IR or Raman active, or IR active in this case, because let us find out whether the A1 mode is IR active or not. So this is what we will do. We will work out the answer for the A1 mode first. So now we know that psi 1 in this case is always when we when we wish to find out whether a given vibrational mode is IR active or not, we have to take the ground state as the most symmetric state, and psi 1 will always be now A1 of A1 symmetry. So we have to do A1, that is ground state, mu x is B1, and psi 2 is the state for which we wish to find out whether that particular vibrational mode is IR active or not. So now since we want to find out whether A1 vibrational mode is IR active or inactive, so we take A1 as psi 2 as well. So then when we do this direct product, A1 into B1 we know is going to be B1, and B1 into A1 is going to be B1. So answer is not equal to A1. Similarly, if we now do the second integral, so A1 for the ground state, mu y, so y is B2 cross A1. So that is going to be A1 into B1, B2 is going to be equal to B2 cross A1, which is going to be equal to, again, answer equal to B2. Then for the third integral, ground state A1, mu z, z is A1, then A1 higher vibrational mode. So that is why we write A1 over here, and this we can figure out easily is going to be equal to A1. So what we see that A1 vibrational mode here essentially is going to be IR active because this particular integral over here gives us the totally, or this particular integral forms basis for the most symmetric irreducible representation, and that is why this integral is going to be non-zero, or it will have non-zero value, and we can tell that this vibrational mode is going to be, or both these vibrational modes which have A1 symmetry, or which transforms as A1 irreducible representation, are going to be IR active vibrational modes. So now let us find out whether the other vibrational mode, that is the V1 vibrational mode, is IR active or it is IR inactive. So for that we have to do is that we have to change the symmetry of the vibrational mode over here. So we write V1, V1 and V1 over here, and let's figure out the answers for these direct products. So A1 into V1 is going to be equal to V1, we know, and cross V1 over here. So again we know when we multiply the irreducible representation with itself, and when it is one dimensional, the answer is always going to be A equal to A1 irreducible representation. So we now have figured out that this vibrational mode or vibrational mode of V1 symmetry is also going to be IR active because we get this integral. It forms basis for the most symmetric irreducible representation, and that is why this integral will have non-zero value. So similarly, if we do for these two as well, A1 into B2 is B2 cross B1. So B2 cross B1, we have, or we can figure out 1 into 1, minus 1 into minus 1, 1 here, minus 1 over here. So that is A2, which is not A1, and that is why this transition is not going to be again Y polarized. And the third one over here, A1 cross B1, answer is going to be equal to B1. So again, we have found that this transition is this particular integral has non-zero value because we have the direct products. The answer of these direct products is equal to A1, and this forms basis for the most symmetric irreducible representation, and that is why the B1 or vibrational mode of B1 symmetry will also be IR active now. So all the three vibrational modes in water molecule we see that are IR active. Now one more particular aspect that we can see is that if we take, say, let us take a hypothetical molecule for which one of the vibrational mode has A2 symmetry. So if we do again these integrations for a vibrational mode which has A2 symmetry, just to show you a very important point here is, let's find out the answer of these direct products. That is, mu x is going to be B1, A2, B2, A2. This is A1. So when you work out the answers of these three direct products, you will find that none of these are equal to A1. So none of these integrals essentially forms basis for the most symmetric irreducible representation in C to B point group. If we take now that this the excited state or the vibrational mode in a hypothetical molecule has A2 symmetry. So what we can see from here, or why we have done this particular exercise, is that when we take either A1, B1 or B2 as the excited states over here, we will find always that one of these integrals is going to be non-zero, or what we will find is that the integral for which we find out, say when we find out for B2, a vibrational mode which has B2 symmetry, we will find that it is going to be non-zero along y direction, or the integral with mu I will have non-zero value. Similarly, when we have a vibrational mode which has A1 symmetry, we will find that this is going to have non-zero value along z direction, or the integral with mu z will have non-zero value. And if we take the vibrational symmetry of the vibrational mode as B1 uh, symmetry, then we will find again that the integral with mu x will have non-zero value, and that will transform essentially as the most symmetric irreducible representation. But when we took A2 as the symmetry of the vibrational mode, we saw that neither or not all the integrals along mu x, mu y, or mu z were, they did not transform as the most symmetric irreducible representation, and all these integrals are essentially equal to 0. So this happens because the particular integral will have a non-zero value only when, or a particular only when both psi1 and psi2 essentially transforms as the same irreducible representation, or gamma psi1 must be equal to gamma psi2, or otherwise the integral is not going to is going to have, the answer is going to be equal to 0 for that particular integral. So that is why, in order to find out whether a given vibrational mode is IR active or not, a very straightforward way is there. Without doing the calculations, one can find out whether a given vibrational mode is going to be IR active, and it is going to be polarized in which particular direction. So for example, a B1 mode is going to be IR active because the X transforms as B1 B1 irreducible representation, and that is why the B1 vibrational mode is going to be always IR active, because X transforms as B1, and we will have this essentially be equal to non-zero. It will give us a non-zero integral. And we also know that this particular integral, that is the one containing the mu x, will have non-zero value, and that is why this transition from A1 to B1 will always be along, it's going to be x polarized. Similarly, we can also say, by looking at the character table itself, that these three vibrational modes, or vibrational modes which have these three symmetries, will only be IR active. This one, the vibrational mode with A2 symmetry, is going to be IR inactive. So this is a very straightforward approach to find out the whether a given transition is IR active or IR inactive. Now, in order to find out whether a given transition is going to be Raman active or Raman inactive, what we have to do is that we have to change the transition moment operator, and instead of taking the electric dipole moment operator, now we have to take the polarization tensors, and there are 6 essentially polarization tensors, and we have to carry out 6 integrals. That is, we have to do mu x squared psi 2, we have to do psi 1 mu y squared psi 2, psi 1 mu z squared psi 2, as well as we have to do psi 1 mu xy psi 2 d tau. All everywhere we have d tau, and psi 1 mu xz psi 2 d tau, psi 1 mu yz psi 2 d tau. So we'll have to do these integrals, and if any one of these integrals again form basis for the most symmetric irreducible representation in that particular point group, then that particular the transition or that particular vibrational mode is going to be Raman active. So we can again find out for water molecule which particular vibrational mode is going to be Raman active and which is going to be Raman inactive. So we can take we know now since mu x square will essentially transform as x square and mu y square will transform as y square and so on. Mu xy, xz and yz will essentially transform as xy, xz and yz, and that is why we can write the irreducible representations for those respective the quadratic functions for mu all these polarization tensor operators. So that is, let us find out whether psi 1, so again 2a1 plus b1, these are the vibrational modes, symmetry of the vibrational modes in water molecule, and we will find whether these vibrational modes are Raman active or inactive. So mu x squared psi 2 theta. Let's find out whether this integral forms basis for the most symmetric irreducible representation or not. So psi 1, again we will take it as a1 because ground state is most symmetric, and mu x square because it transforms as a1, again a1 over here, and psi 2 we know now we want to find out that whether a1 vibrational mode is non-active or not. So that is the excited state, it has the symmetry again a1. So the answer is going to be equal to a1, and we now know that this particular vibrational mode is going to be Raman active as well. We can do again all the other integrals, rest 5 integrals, that is with the other polarization tensor operators, and we will find out that answer to all these z square and y square, because they also transform as a1, will essentially give us answer equal to a1. So then again we can find out for the b1 vibrational mode whether it is going to be Raman active or not, and let us do again b1. For b1 we see if we do mu xz, that is a1 is the ground state, mu xz transforms as b1, and b1 vibrational mode over here. So a1 into b1 will be b1 over here, and then b1 will be left, and the answer is going to be equal to a1. So now what we have seen that even the b1 vibrational mode in water molecule is also Raman active, and we see that it is polarized along the xz plane, because we could tell beforehand doing the calculations, because we know that the b1 transition, b1 or vibrational mode, we see that even the xz function transforms as b1, and that is why in this case when we did this integral we got answer equal to a1. If you do it for the other polarization tensors, that is for xy, x square, y square, z square, xy as well as yz, the answer is not going to come out to be equal to a1. But in any case, since one of the integral essentially out of the 6 integrals that we will have to do for b1 vibrational mode is transforms as a1 irreducible representation, and that is why this particular vibrational mode we can say is Raman active. So, but you need to work out all the integrals. You must remember that one needs to work out all the integrals to figure out the answer essentially. But what we have taken a shorter route, and we just here found out the integral which essentially gives us the most symmetric, or which forms basis for the most symmetric irreducible representation, because that we could tell by just looking at the character table of the point group. So this essentially, by looking at the character table and just when we derive the symmetry of the vibrational modes, and from there by looking at the character table for the point group of that molecule, we can easily tell whether the particular vibrational mode is going to be IR active or whether it is going to be Raman active, because we can sort of simply figure out these things by looking at the character table itself. So this essentially brings us to the end of this lecture, and what we have learned here during this lecture is to find out whether a given transition, whether it is electronic transition or whether it is magnetic spin transition or whether it is a polarization transition, we can figure out whether the transition is going to be symmetry allowed or symmetry forbidden, or we can find out the symmetry selection rule for that particular transition. And then we can also we have learned how one can figure out, or how one can find out whether a given vibrational mode of a molecule is going to be IR active or IR inactive. So in the next lecture we will learn more applications of group theory, and this let me conclude this lecture with this, and I thank you very much for being with me during this lecture.